The development of the Moon has long been explained by the theory of a massive collision between Earth and a celestial body named Theia. This event supposedly led to the formation of the Moon over millions of years. While the Moon has been a tranquil presence in the night sky, recent observations suggest it is undergoing alarming changes. Seismic activity and mysterious alterations in its surface may point to a potential disaster. Could these lunar shifts trigger catastrophic events on Earth? What chain reactions might occur from our lunar neighbor? And how could these changes affect life on Earth? The Apollo 11 mission marked a significant milestone in space exploration, not only for landing the first humans on the Moon but also for bringing back precious lunar rocks and dust. The astronauts returned with around 1.6 kilograms of material, which soon became crucial in unlocking the mysteries of the Moon's origin. Upon studying these samples, scientists found that the lunar rocks date back approximately 4.5 billion years, a crucial discovery that confirmed the Moon formed around 150 million years after the creation of our solar system. This period, known as the Late Heavy Bombardment, was one of the most chaotic in the history of our solar system, with numerous small planets colliding, leading to the formation of Mercury, Venus, Earth, and Mars. It is believed that one of these cataclysmic collisions resulted in the creation of the Moon. The impact theory suggests that when Theia collided with Earth, the collision shattered both bodies into countless fragments. These fragments, along with debris from Earth's mantle, slowly coalesced to form a molten disk, which eventually solidified into the Moon. For decades, this theory has been the leading explanation, first proposed in the 1970s. However, recent research has cast doubt on this long-standing narrative, suggesting the Moon's formation might not have been gradual but rather occurred in a much shorter time frame. A key assumption in the traditional theory is that the Moon is primarily made of material from Theia. However, analysis of lunar rocks challenges this idea. The composition of the lunar rocks is strikingly similar to that of Earth's, rather than being more akin to Theia or other celestial bodies. Moreover, the isotopic signatures found in lunar samples resemble those found on Earth, differing significantly from those seen in Martian or other solar system bodies. This evidence suggests that much of the Moon's material came from Earth. Another intriguing aspect is the alignment between Earth's rotation and the Moon's orbit. Both share similar orientations, a detail difficult to explain if the Moon were largely composed of debris from Theia. These discoveries have led some scientists to propose that the Moon's formation might have been a rapid event rather than a slow process. One hypothesis suggests that the collision between Earth and Theia was so violent that it caused an enormous explosion, hurling material into space at high speeds. This material could have coalesced into the Moon within just a few hours, which would explain the shared composition and isotopic similarities between the Earth and Moon. If the Moon formed so rapidly, it could reshape our understanding of planetary formation processes. Such a scenario would suggest that other moons and planetary bodies in our solar system might have formed in similar ways, challenging established ideas about the slow development of planets and moons. To explore these alternate theories, researchers turned to a powerful computer program known as QUIC, which simulates the complex gravitational and hydrodynamic forces at play during such a massive collision. The team used a supercomputer named CASMA to run simulations, testing various impact angles, velocities, and sizes of the colliding bodies. They modeled up to 100 million particles to replicate the matter involved in these catastrophic events. These high-resolution simulations provided a more detailed view of the collision dynamics than ever before. The results were groundbreaking. In contrast to the traditional belief that the Moon formed over a long period of time, the simulations indicated that the Moon could have coalesced from the debris in just a few hours. This finding challenges the previous understanding of the Moon's formation timeline. Furthermore, the simulations revealed that much of the material that formed the Moon's outer layers originated from Earth, providing deeper insight into the Moon's composition and its close relationship with our planet. These detailed simulations were conducted by refining the impact parameters to achieve highly accurate results. The team discovered that Earth's material played a vital role in the Moon's formation, reinforcing the notion that the two bodies are intimately connected. By recreating high-energy crashes and testing various scenarios with extreme precision, the researchers demonstrated that the Moon's formation could have been a rapid event, appending previous theories that it took millions of years. In summary, these new findings suggest that the Moon may have formed much faster than previously believed, with a significant portion of its material coming from Earth itself. This discovery could alter our understanding of planetary formation and prompt a reassessment of how moons and planets evolve. A new hypothesis suggests that the Moon could endure dynamic forces, potentially pushing it into a higher orbit. This theory helps explain the Moon's elliptical orbit, thin crust, and partially liquid interior. However, to validate this hypothesis, scientists need to examine rock and dust samples from deep beneath the Moon's surface, which remain a key focus of ongoing lunar exploration missions. These efforts will help confirm computer simulations and enhance our understanding of the Moon's formation and its relationship with Earth. The simulations provide a clearer picture of the Moon's evolution over billions of years. Accessing deep lunar samples is crucial for advancing current and future lunar missions, allowing us to validate these simulations and refine our understanding of the Moon's structure. This research not only advances our knowledge of the Moon's origins but also offers insights into planetary formation and evolution within our solar system. Unlike Earth, which has been reshaped by various geological processes, the Moon preserves ancient records from the early solar system. The Apollo program, initially driven by Cold War competition, left a lasting scientific legacy by returning 382 kilograms of lunar rocks and soil. These samples provided insights into a massive collision between early Earth and a hypothetical body called Theia, which led to the formation of the Moon and influenced Earth's development. The Moon's surface, untouched by erosion or tectonic activity, serves as an immaculate record of the solar system's early history. Future lunar missions aim to explore untouched areas and collect additional samples to further uncover the Moon's history and evolution. Examining the Moon is crucial for understanding Earth's history, and ongoing and future missions will continue to unravel the mysteries of our origins. William Hartmann's 1974 theory proposed that the Moon formed from debris ejected after a catastrophic collision between Earth and a body called Theia, reshaping our understanding of lunar origins. The impact caused Earth to spin faster, and debris from both Earth and Theia was launched into space, eventually coalescing to form the Moon. During this violent process, volatile substances like water were lost, leaving the Moon dry. The Moon's composition is primarily derived from the mantles of Earth and Theia, which explains why it is less dense than Earth. While the Moon has a solid iron core, it is much smaller than Earth. From its tumultuous beginning, the Moon gradually cooled, and its liquid surface solidified. However, it continued to face intense bombardment during the chaotic early solar system. This bombardment is evident in the global elevation map created by the Lunar Reconnaissance Orbiter, which illustrates the extensive impacts the Moon has endured. The Apollo astronauts encountered rocks formed from volcanic activity, a secondary effect of the numerous impacts. These volcanic rocks, shaped by ancient volcanic cycles, reveal that the Moon was not always the lifeless, barren place it appears to be today. Further studies have provided insights into the Moon's geophysical properties. Seismic data from the Apollo missions revealed that the Moon experiences moonquakes, strong enough to cause significant changes in its crust. These quakes are believed to result from tidal forces exerted by Earth's gravity, further highlighting the complex gravitational relationship between our planet and its satellite. The Moon's lack of atmosphere means its surface is directly exposed to space, enduring impacts from micrometeorites and solar wind. Over time, this has transformed the lunar surface, creating a fine dust layer called regolith. The regolith contains tiny glass beads formed by the intense heat from micrometeorite impacts, preserving a record of the Moon's history of space weathering and volcanic activity. On Earth, volcanic eruptions are often driven by water, which is heated and compressed by the movement of large tectonic plates. However, the Moon lacks this hydrological mechanism, so its volcanoes are connected to impacts powerful enough to melt the surface and release material from its hot interior. In the lower gravity of the Moon, volcanic eruptions took on a different form. Lava would have splattered high above the surface, creating thin, smooth layers that spread out from the eruption site. These layers eventually formed the Moon's Maria regions, covering about 1/16 of its surface. Scientists believe these large volcanic basins originated from massive impacts that occurred 3 to 4 billion years ago. The materials raised by these impacts were composed of heavier elements that initially sank into the lunar magma sea. Modern technologies, such as lunar cameras, have helped scientists identify volcanic deposits in recent impacts, providing valuable insights into the Moon's geological history. The Moon's volcanic history and its effects on Earth offer intriguing clues about its geological and impact history. Notable features such as the Aristarchus Plateau, with its lava-cut channels and volcanic glass deposits, and the Tycho crater, with its towering central peak and evidence of impact heat, stand out as remarkable examples. The Moon's gravitational pull also influences Earth's rotation and contributes to ocean tides, underscoring the interconnectedness of their histories. Water on the Moon is a complex subject. Initially thought to be dry due to the giant impact hypothesis, recent findings suggest the presence of water ice, particularly in the Moon's polar regions. Studies indicate that water may have arrived via comet impacts or been present in volcanic glass beads. Discoveries by missions such as India's Chandrayaan, NASA's SOFIA, and China's Chang'e 5 have found evidence of water in lunar soil and rocks. Water ice is believed to be abundant in permanently shadowed craters at the Moon's south pole, potentially holding enough water to support future lunar bases. NASA's Lunar Reconnaissance Orbiter and upcoming missions, such as Artemis, plan to further explore these icy reserves. Establishing a sustainable human presence on the Moon will depend on utilizing local water resources, which are crucial for long-term exploration and habitation. Neil Armstrong's pioneering lunar landing in 1969 highlights the monumental significance of human space exploration. Armstrong's transition from a skilled pilot to the first person to walk on the Moon showcases his contributions to aviation advancements and his lasting legacy. The Apollo 11 mission marked a historic moment on July 20, 1969, when Armstrong and Buzz Aldrin set foot on the lunar surface, with Armstrong famously declaring, "That's one small step for man, one giant leap for mankind." During their 2.5 hours on the Moon, they conducted experiments, deployed scientific instruments, and left behind a plaque commemorating their visit. Their safe return to Earth on July 24, 1969, was celebrated globally, cementing their place as legends. Despite the acclaim, skepticism persisted, with theories suggesting that the Moon landing was staged. These theories were fueled by anomalies like the movement of the American flag and the appearance of the lunar environment in photos and videos, casting doubt on the authenticity of this extraordinary achievement. The astronauts' involvement in the public narrative and the immense pressure to maintain a specific story may have contributed to their anxiety.